from today, Dr. Cornelis Stal. Dr. Stal is a lecturer and researcher at Ghent University of Applied Sciences and Arts, Department of Built Environment, also digital manager of Heritage Program from Greece, and visiting professor at Ghent University Department of Geography. Our guest has a significant experience in the field of combination, processing, and quality analysis of airborne and terrestrial laser scanning and photogrammetry for 3D modeling. Currently, he has a special focus on the digital 3D documentation of cultural heritage and the management and publication of these data in online environment. Given his experience in heritage, he managed the heritage management organization, as I said, from Greece, where he participates in multiple research projects and summer schools. Actually, this is how I had the pleasure to meet Cornelis Stal. And today's lecture will explore an exciting subject about the uses of geomatics and spatial images in archaeological investigation and what information it can provide for a better research. The Q&A section will be after the presentation, and since Dr. Stal already gave us the permission to register this presentation, it will be available on our social media software. So please, you have the floor.
Thank you very much for this introduction. Good morning, everybody. Yeah, I can actually skip this this slide with my introduction. One thing that was not mentioned, however, is that I'm also a very proud member of the research team of the Sultana School of Archaeology. So in the previous years, I participated in some of the schools, especially with Christina and Ovidio on the documentation and the acquisition of airborne data. And in a few slides, I will also demonstrate some of the work that we have been doing there together. So this presentation, a little outline of what I'm going to talk about. First, I would like to give you some applications of geomatics for archaeology and digital humanities. So the projects that I was happy to collaborate in, with a special focus on the data acquisition and the data processing. So myself, I'm a land surveyor. I'm a geomatics specialist. I'm definitely not a specialist in archaeology or digital humanities. But I think it is by combining at least these two disciplines, geomatics on the one hand and archaeology, digital humanities on the other hand, that we can really add value to both research disciplines. And then in the second part of my presentation, I will give you an overview of some of the software packages that I'm using or that I'm going to use on the specific topics on data acquisition, spatial data processing, point cloud processing, conventional and linked data and image processing. And for these different topics, I selected some software that I would briefly introduce to you. And then, of course, a conclusion, a roundup, where I will also give you a summary of all the software packages and some promotion for the summer school that we are going to organize with the Heritage Management Organization in Greece in the coming May and June on GIS, photogrammetry, and laser scanning. So for a couple of decades ago, there was, of course, already GIS software, there was some photogrammetry software, there were some database exploration software available. But typically, these software packages were quite expensive. If you go for commercial GIS packages, you will go to several thousands of euros for at least for a commercial license. Nowadays, these commercial packages are more cheaper because of the need for research licenses. So the price has significantly reduced for research institutes like the institutes that we are working on. But on the other hand, we also see for 10 or 20 years that there is a large and daily growing community, very active community, that is active on the development of open source software for these various topics. So we're talking here about GIS, we're talking about photogrammetry, image processing, point cloud processing. And the interesting thing here is that many of these initiatives, many of these development projects, that's also a combination of experts from the ICT research discipline, so hardcore programming experts, geometric experts, but also on the demand side, you will see a lot of archaeologists and digital humanities experts there. So it's a very nice interdisciplinary community that is working and developing these open source software that are just freely available online. If you go to GitHub, you will be exploded by, overrun by a lot of code and a lot of programs that are freely available for all kinds of applications. The availability of these software, in some cases, they come with a graphical user interface, a GUI. So you will have a screen with buttons, with options that you can interactively set. But in many other cases, you will have to work with a command line or a terminal in Windows, Linux, or Mac OS. Otherwise, you will find programming code or bindings. So most of these codes are written in C or in C++. And then bindings will actually allow you, for example, via Python, to access all these models, all these libraries that will give you the functionality of the specific software. Something that I will not discuss today is software as a service, or SaaS, and APIs. So SaaS is, of course, software that are available somewhere in the cloud and that will do the processing, the data processing for you. Actually, the last example of the software that I'm going to show you is more or less can be implemented as a software as a service, but also APIs, programming interfaces, application programming interfaces, also very useful for interaction with online resources, and that's also something that we will not cover today. So given these different options for availability, we also have to look at installers. How can we install these programs? Or you just click and play. And in many cases, you will see like OSGeo for Windows applications. So if you want to extend your GIS environment, you can use that installer to add functionalities to your GIS environment. pipconda, if you're into Python programming, frequently used library managers. And for macOS users, Homebrew is definitely a very interesting program to do your package management. But before I go into these software topics, I would like to give you some examples of applications of geomatics for archaeology and digital humanities. So focus a little bit on applications. So let's get started in Belgium, the place where I'm living. I'm actually from the Netherlands, but I live in Belgium for, I think, already 14 years, not far from Ghent. You see a wonderful picture of Ghent. And one of the nice examples that was actually one of the first applications of 3D modeling was the reconstruction of a virtual globe. So a globe made by Gerard Mercator from 1551, I think. You can access the virtual representation using this QR code. It's all tested, so that should normally work. But the aim here was to make a 3D model, also a textured 3D model, of course, so that all the cartographic information on the globe was visible there. And then that model would be some kind of a reference data set for the restoration of that globe. Here, another example, the use of digital elevation data derived from airborne laser scanning. If you have your data, you make a digital elevation of it, then you do some filtering, some image enhancement. Here you see a nice example of a sky view factor analysis as implemented in Saga GIS. And then you can really see all the little artifacts, here we're talking about trenches, World War I trenches, foxholes. So wonderful applications of the use of spatial data for landscape reconstruction. Another application, landscape reconstruction, contemporary map, a reference map with a little river, little stream, and then based on historical material where you can see how the river was flowing in the late 1800s. Assume that we want to make a reconstruction of that river. What is the impact of that reconstruction on the nowadays parcels and the buildings that are situated on that site? So you can use GIS to do intersections and buffer analysis and all that kind of analysis. Now let's go from Belgium to another country, to Mexico, in Central America. That was one of the first large-scale projects where we implemented airborne photogrammetry. And I'm not speaking necessarily about drones, because we also worked here with helium balloons, just as an experiment, if that would work there. And actually, it was quite successful. So here you see an example of the Maya temple of Etsna, the Cinco Pisos temple, also again with the QR code. And interesting here, this was made by the time that commercial drones were still quite expensive. So if you want to have a drone for photogrammetry, you should think about 10,000 to 15,000 euros. So in order to find or to overcome that financial difficulty, we actually built our drones ourselves. So the drone that you see here is a fully homemade drone. I think for 2,000 or 3,000 euros, we were able to manufacture that drone ourselves. So we had multiple of them for testing, and then eventually also for operational purposes. In this case, in Mexico. Of course, 5 years later, with all the DJI drones, the Mavic, and the Phantoms, it's not really necessary to build your drone yourself. For the same price, you will have a fully operational, high-quality drone that can fly in the air for 25 or 30 minutes. So why build your own drone? And you can actually now just go take your drone and fly for half an hour instead of, in this case here, 15 minutes. But still, the results and the techniques behind it are still the same. So you see here the temple, some other examples of the data that we acquired there, point clouds, meshes, textured meshes that were then eventually sent to the Ministry of Culture for their inventory of the archaeological sites there. The cool thing about 3D modeling, and especially 3D modeling and image-based 3D modeling, is that even if you just have a smartphone and you're walking there as a tourist or as somebody that's working on a data acquisition campaign, that you can just take your phone, make your photos as if you're working with a professional high-grade digital camera, and that you can then just process your data in the 3D modelings, in your 3D modeling software. And if you master these tools, it is very easy to make a virtual repository of your 3D artifacts that you have been visiting. So for example, if you go here to this website, it's Sketchfab, and on Sketchfab you will find many repositories of people that have made 3D models and that are interactively available online. So instead of making pictures like all the tourists do and put your pictures on Facebook, you can actually make 3D models, holiday 3D models of cultural heritage artifacts. So it's not only for fun, but it's also some more serious implications of data acquisition. Then also in that area, we went to Honduras, to Piedras Negras, not far from the Maya site of Copan. And in this case, that's the reason why I wanted to show you this one. We still use the same drone. So this is also a homemade drone. But instead of working only with a conventional camera, so a camera that is able to capture yeah, the normal human eye sensitive colors, or the spectral that we're able to see. So the conventional channels. We converted one of the cameras. So we removed the hot mirror, and by removing the hot mirror from a camera, you can make your camera actually sensitive to the near infrared signal. And if you have your near infrared signal, or if you're able to capture the near infrared signal of your environment, you're actually able to calculate vegetation indices because of the reflection of near infrared by healthy vegetation and the lack of near infrared by the absence or non-healthy vegetation. And if you have a model like that, or an orthophoto or 3D model of that, you can actually work on crop mark detection. And crop mark detection is then saying something about the potential of objects being under the ground, where vegetation differs from its direct environment. So it's a very useful tool to do archaeological prospection that we implemented here for the first, or at least for us, for the first time. It's also very nice to be there in a very interdisciplinary team, the Copan of the Piedras Negras project. There was, at a certain point, there was a guy that was working on artifacts and the interaction between different sites. So there was an artifact found on the site here, and there were artifacts found on the site here, and on the site here. And he was able, based on the characteristics of these artifacts, I think it was they were lithics, and by the characteristics of these lithics, he was able to identify relations between different sites. So if you master your GIS applications, you're actually able to make some kind of a roadmap, a hypothetical roadmap, how the traders or the people would go from one site to another. So if you have the different sites here scattered by points, behind it is a digital elevation model. Of course, if you want to go from one side to another side, you will not take a straight line, because it may be too steep, or there would be rivers on your path. But you will take the route with the least cost. And if you have the route with the least cost, and you do that for all the sites to all the other sites, you can actually make some kind of a density plot of your routes, where a lot of roads, a lot of potential roads, I should say, a lot of potential routes are intersecting. And that could be the basis of some kind of archaeological potential mapping. So this was a purely hypothetical exercise, but still very nice to as an application of GIS. And then again, yeah, she already showed you in Mexico. You're working on this stone masonry mask in the National Museum of Guatemala. There was also this wonderful bas-relief with these Maya signs that somebody was able to identify and to explain. And I made an orthophoto also, again, with my cell phone. So just as a cool application of 3D modeling with your smartphone. Now let's go back to Europe. As a master student and as a PhD student, I collaborated a lot with the researchers on the archaeological site of Torikos in Greece. It's not far from Athens. So actually my very first archaeological campaign, I was invited to participate on this archaeological site. So it was in 2006, I think, or 2006 or 7. And that was also actually the seed for me for my interest in this wonderful discipline. And some of the things that I did there, or that we did there, I should be honest about that, we did there, was take our drone and just make conventional orthophotos and 3D models. So these are just typical applications of airborne imagery. Put it in Agisoft, get your orthophotos with some ground control points that are topographically surveyed. And these are actually used as a base layer, base map for the research that came afterwards. So this is a snapshot of the environment, and using that snapshot, the archaeologist or the main archaeologist can actually start planning his excavations and do a follow-up of the activities that take place on that site. So if you have your base map, here another example of a follow-up of an excavation. So this project here, also in Torikos, there was an excavation near a cistern, and every day just before the archaeologist starts excavating, made a 3D model of the status of the sites, and every day you will see in a 3D visual how the site was actually developing. And then with the help of the archaeologists themselves, we made a high-res matrix. So this is actually a platform where you can click on a certain context, and then the context will allow you to zoom in to that specific area in the 3D model, and you will get some basic information about that site. And it's also published in an article in the Journal for Archaeological Science. So wonderful application of 3D modeling, archaeological site documentation, and some metadata and data that is attached to this data model. Well, if you have your orthophoto derived, for example, in this case from UAV airborne data, then I already told you, or already mentioned, that this is a wonderful base layer for further geographical exploration and archaeological exploration. So this is, for example, a map, a stone map that was being generated in the 60s. We georeferenced it, put it on the orthophoto, and then somebody else was able to identify and to date the different walls. So it's actually a time layer where you can just focus on certain periods of eras of the archaeological site. Then more recently in Crete, we worked on a project on the island, the little island of Psira. So it's in not far from Agios Nikolaos, in the Bay of Agios Nikolaos, near Mochlos, a Minoan site, Minoan harbor site, where the American School for Eastern Crete Studies, Institute for Eastern Crete Studies, INSTAP, is doing a lot of research in that area. It's also collaboration with the University of Western Attica. And what these researchers are doing is actually documenting the follow-up of the archaeological site of Psira. So on a yearly basis or on a systematic basis, they go on that site with their plans, and they're drawing a lot of information on that map that tells the user something about the deterioration of the site. So if there are plants growing, if there's soil erosion, or if there's just a collapse of the wall. So this is a lot of data, a lot of manuscript data. And the idea here was to convert that manual process, that manuscript process, to a digital process. And then the geomatics comes in handy, where you can digitize everything, all these different plans. Of course, when you do that once, you do it twice, you do it 3 times. That's a lot of fun. But if you have to do it 15 times, you will start looking at finding ways to automate that process. And in a few slides, I will elaborate a little bit more on how we accomplish this data processing automation. And the result of that, this is a preliminary result, is a fully digitized, vectorized reconstruction of the archaeological site. And instead of doing everything on manuscript plans, the researchers and the conservators are now just able to use their tablets, draw lines, make notes, and have it directly in a spatially georeferenced database. Another very cool example is the archaeological site of Papadiocampos. It's also a project in collaboration with the Study for Eastern Crete, the Eastern Crete Study Center. But in this case, it was the first time for me as a lecturer at Hoogent to invite students, so land surveying students, and let them work in the late sun of October to work on the documentation of archaeological sites. So the students that you see here, I think we were with 25 students in total. They are used to do property surveying, construction surveying, and this was actually for most of them the first time that they also got involved in archaeological documentation. So very excited about that project. I think we had 5 or 6 sites. The students were divided in different groups, and their task was actually quite simple. Every group got an archaeological site assigned to them, and their task was to make a 3D model by the things that they learned in the last few years in their educational program. There were also some international students that joined us in that campaign. So it was a very interesting interaction with international students, but also the more technical civil engineering, let's say civil engineering student or civil engineering land surveyors, and the students from other disciplines. And the results are actually quite nice. Just mentioned in the pre-discussion about a web server that is being implemented at Hoogent. Well, the data that we obtained at this site of Papadieu Campos is available. If you go to this website, you will actually access the website that we built after the project, geo.hoogent.be/create, and you will be able to see orthophotos, digital elevation models, interactive 3D models, and point clouds. So it was a wonderful opportunity for both myself, the team, and the students. And then, of course, advanced GIS analysis. In this case, this was an exercise on peak sanctuaries and the intervisibility of peak sanctuaries. So scattered over Crete, you have different peak sanctuaries, so sanctuaries that are situated on higher points in the landscape. And by using digital elevation models like Aster data or SRTM data, you can actually calculate what sites are visible from any other site. And that will actually allow you to end up with a network of visibility lines. It's also a nice example of GIS. So I'm also almost finished with my applications. Here the last one is a project that we did not last September, but the September before COVID in southeastern parts of Turkey, in Tur Abdin. So it's actually an area that is historically very multi-ethnical. There are a lot of Syriac people, so very ancient Christian community that have lived there for many centuries. Due to the political and ethnical problems there in that region, many of them have fled in the 20s, the 30s, and even more recently in the 90s, leaving behind a lot of cultural heritage. And then the idea of this project was to go to that area and make a snapshot of the cultural heritage of the Syriac community. So we modeled a lot of churches, monasteries, and other artifacts in that area, put them available online. So we built a website that is unfortunately currently offline. But the idea of that website is to show the people that are in diaspora, in Sweden, in Germany, in the Netherlands, and in Belgium, and in the United States, to show these people in diaspora their own cultural heritage, so that they still get this sense of community building, and that they see, okay, this is the situation, this is the this is actually our history of that that is still there. And many people are also coming back and get involved in the restoration and the maintenance of these artifacts. So on that website, if it was online, yeah, you will see, of course, a lot of heritage reports about the status, about the meaning of these different artifacts. But I was happy to participate in that project in the construction of 360 panorama photos, 3D models, and even virtual reality applications. It was the first time that I did some experiments with that, and quite exciting. Actually, the slide that you see here, this is a virtual reality application if you have your virtual reality goggles and you aim at a certain cylinder that you see here, you're teleported to that area and you can see the entire 3D model in VR, which is quite exciting. So these are some screenshots of the website with information, with access to the reports and the different other deliverables. And then, of course, last but not least, the Sultana project that you are working on. So these are some orthophotos and digital elevation models that we obtained in that we obtained in the first year that I was participating. Here the drone or video's drone and the Proud Flyer. So a wonderful collaboration on the acquisition of spatial data, delivering highly accurate georeferenced spatial data in terms of orthophotos, 3D models, and digital elevation models. But also, given the fact that much data is already also available online, it is a wonderful site also to do analysis of historical cartographic material. So I don't know exactly the metadata of the different maps, but there are contemporary maps from the 90s, the Soviet Russian maps from the 80s, and then here are some maps from the early 20s and the late 19th century. And by putting all these data on top of each other in a spatially coherent coordinate reference system, you're actually able to make some kind of a time series of these different maps and see how the landscape evolved over time. And especially here in the Mostiche Lake, I'm sorry for my bad pronunciation, it is very interesting to see how the different land uses and the different topographic systems have changed in that area. It's all aided by cartographic time series analysis. And also in the entire area, as you know much better than I do, there's a lot of data acquired, manuscript data acquired in previous decades. Like for example, here, if I'm not mistaken, this is from the 60s, all available in books, in libraries. If you make scans of it, if you make photographs of it, and you are able to situate these sites in the contemporary landscape, you take your GPS, make a georeferencing, make a digitizing of it, assign attributes to the different features, and you can actually make a full digital repository of historical excavations as well. So I think in this case, GIS is a wonderful tool to facilitate that digitalization process. And a last example here, digital site management. On a certain day, there was a drone flight over the site, and we start drawing polygons on the different pits that were excavated. And yeah, possible idea would be to assign identifiers and attributes and actual meaning to these different artifacts. It's more hypothetical exercise that we did here, but I think there's a lot of potential on expanding that and making a full digital site management application for the site of Sultana. So voilà, these were my my applications. I would like to continue now with first a sip of coffee. And open source GIS software. So if you're talking about open source software for GIS applications, most of the people will indeed think about QGIS. I think it's the most widely used GIS application for GIS. Of course, there are many commercial packages. I think the most famous commercial GIS application comes from Esri, like ArcGIS, ArcGIS or ArcMap, but that's the commercial environment. I'm talking here about open source software. So then, of course, QGIS comes in mind. which is free and open source geographic information system for the creation, edit, visualization, and publishing of spatial information. And it's very good to mention that this software package is available for Windows, Mac, Linux, BSD, and even mobile devices. As we speak, a colleague from Hogent is testing an application that that we prepared together for the documentation of trees in a certain municipality here in Belgium. So that project was fully prepared in QGIS, then exported, and he's working in QFields. So actually on his smartphone, he's able to do documentation of conditions of trees in a certain municipality. So actually take your GIS system and go on site. Since a few years, and actually I'm quite grateful for that, for participating in the Sultana project. There are some people here working on Mac computers. I was never very aware of Mac, but since a year and a half, I bought myself a MacBook. So all the software that I'm presenting here, I also tested it on my own MacBook. So QGIS is definitely a very interesting package also for Mac OS. It offers basic functionality that you can expect from a GIS environment. And even if this basic functionality is not sufficient, you can actually supplement it by a large series of plugins, for example, to draw profiles, to do cluster analysis, to get access to APIs and online resources. That's all available via plugins. It has a very fast update rate because of the fact that it's the most commonly used open source GIS environment. It also comes with a large community, which is also good if you want assistance for a certain specific tool. Put it on a forum somewhere and you will get an answer quite fast. It is available in many languages, in English, in German, French, Dutch, and I think also in Romanian. Didn't test that. And it supports many data formats. So if you buy a commercial GIS environment or you buy a license for a commercial GIS environment, frequently you will have to buy for an addition, or you will have to pay an additional fee to import GML or to access WFS services. Well, this is all integrated in the standard QGIS environments. What many people don't know, however, is that if you have your QGIS environment installed, that you also have access to some other software packages like Saga and Gras. Saga and Gras are two independent software packages that are also open source. And since a few years, these software packages are integrated in the QGIS environment. So actually, Saga, I use it, or both Saga and Gras, I use it a lot for image analysis and terrain analysis. And these tools can be directly accessed via your standard QGIS interface. Well, behind this this interface, behind this graphical user interface, there is a library called Geometry Engine Open Source, or GEOS. And GEOS is actually a C++ port of a subset of Java topology suite, GTS. And it's the most widely used geospatial C++ geometry library. It's a very powerful library to access and to manipulate geometrical or geographical objects. And many of the algorithms that are written for QGIS, like buffer analysis, intersections, and all that kind of tools, they are based on this GEOS library. So it will allow you to have a very smooth way of working with spatial operations and to define spatial predicate functions. And on top of that, so you will have your QGIS. Below that, there is this more abstract spatial library. And between, you will actually find the Geospatial Data Abstraction library, a very frequently used tool if you're using QGIS and you open a shapefile or you open a TIFF file, you're actually using the Gdl environment or the Geospatial Data Abstraction library, which is actually a Swiss knife for spatial data. And it will allow you to read and to write raster data, vector data, and even point clouds. For point clouds, I have a dedicated chapter in my presentation, so that will come in a few slides. But the Gdl offers the ability to read, write, and manipulate raster and vector data. And the interesting thing about it is that even without opening your QGIS environment, you are able to work with the Gdl tools in your terminal, in your prompt or in your terminal in Mac. Added here 2 screenshots that will allow you to get access or to obtain access, for example, if you want to merge several raster data sets, or if you want to convert a shapefile to a KML file without opening your QGIS environment. It's a matter of typing the right commands, and then Gdl will do the rest for you. So it's compatible. In this case, I've tested it in both Windows and Mac, but also on Linux and other distributions. It should normally work. So I will explain in the next slide how that actually works by an example. For example, I have here a shapefile. I have a shapefile that I want to convert to a KML file. Well, what I can do, I can open my QGIS environment, open my shapefile, right-click, export data, and then define my my export format. But imagine the situation that I will have to do that for 100 files. Yeah, that's a little bit time-consuming, of course. And in that case, you can use just simple commands where you say OGR to OGR. You define your export format, you define your output, you define your input, press enter, and in a few seconds or less, you will have your output format. The same holds also here for conversion of coordinate reference systems. So if this data are, for example, in the Romanian coordinate system and you want to convert it to WGS84, well, the only thing you will have to do is define your target coordinate reference system with here a reference to WGS84 4326 PSG code. Press enter and the data will be automatically converted from one coordinate system to another coordinate system. And the cool thing about OGR to OGR, so this tool to work with vector data, is that you can actually combine all these different flags, as they are called, or these options, in one run. So if you want to convert a data set from a shapefile in the Romanian system to a GeoJSON in WGS84, you can just combine different flags, the format flag and the target CRS flag, and the result will be actually, in this case, a GeoJSON file projected in the WGS84 system. And if you want to do that 100 times, you can actually loop that process and do that, for example, for all your shapefiles in a specific data folder that I will also show you in 2 slides from here. So that was for vector data, the conversion of vector data. You can also do that for raster data. When we're talking about raster data, there is no tool available like OGR to OGR that is able to do everything in one run, but you will have to use different tools for that. So for example, here the transformation of the conversion from one data format to another data format, that is possible. So for example, here there is a TIFF file, and the TIFF file should be converted to a JPEG, or the other way around. No, it's going from a TIFF to a JPEG in the Belgium coordinate reference system. Then we use the Gdl Translate tool. If you want to reproject that data set, you will have to use Gdl Warp. So it's actually warping your raster data set from one input file to another output file. with a source coordinate reference system to a target coordinate reference system. And if you want to do that in one run, you can actually make a batch file where you put the different tools behind each other, and then possibly work or optionally work with temporary files that you can clean up at the end of your data analysis. So what's actually happening here in this last example, we first convert the data from one coordinate system to another coordinate system. So from the Belgium landward projection to WGS84. And the result of that is written in a TMP file. And that TMP file is then converted to a JPEG. So the result is actually a JPEG in WGS84, and that's cleaned afterwards. A wonderful application where I really start working with this tool, with this series of tools, was the project in Psira. So I told you that, okay, these people are going there every year. They make a lot of manuscript plans. Well, there was actually, to be honest, already some kind of a digitalization process behind that, because in Photoshop they were drawing a lot of polygons, and they assigned a certain color to every polygon, and that color corresponds to a certain type of endangering characteristic of that archaeological site. So that was all in Photoshop. From Photoshop, we converted all these files to TIFFs, to TIFF images that are not georeferenced. So at the end, we had, for example, for one specific building, we had 25 different TIFF files, all in the same, with the same extent, with the same resolution, but the content was totally different based on the implementation and the things that they read in the field. So what you see here in this run, or in this script, this is actually a Windows batch file, is that we converted all the TIFF files in a certain folder from one file to another. So here, all the data, it's actually, the data are actually leveled from a multi-bit to a single byte file. Then there was a translation based on a series of ground control points that are only measured once. So we tested it, or we initiated that process for one file. And the coordinates, or the coordinate pairs that define the relation between the picture coordinates to the real world coordinates, they should only be defined once. So this is actually the translation function. Then we do a warping function, a polygonize function. And at the end of this, you will end up with a shape file where all the different polygons, all the features that were drawn in Photoshop, that they are in, let me check, I think this is the UTM system. So the end is a shape file in UTM where all the different types of degradation are in a spatial digital database. So very convenient. You prepare the script once. You can do it as many times as necessary, depending on the number of TIFF files in your data folder, and you will end up with a huge amount of shape files. Well, this is batching in Windows. Of course, when I want to do that on my Mac computer or on a Linux computer, I will have to rewrite the entire code. And in that case, it might be easier and more convenient to work with Python. Python is a programming language that is used a lot in scientific research, especially by non-informatics people, because compared to the more conventional languages like C or C++, it is very easy to learn, very straightforward, and it offers a lot of options also for specific disciplinary applications. So if you have your Python installed, this is just a basic environment where you can do some basic programming. The good thing about Python is that it can be easily extended by different other libraries. So a library is actually a bunch of code that was designed, or that is designed for a specific aim. For example, here NumPy is designed for fast matrix analysis. Pandas is defined or written for more advanced matrix analysis, where you work with actually more with tables. Yes, Sklearn for machine learning. And there are a lot of libraries that will allow you to do specific tasks using Python. So some of the tasks that I'm using myself a lot for spatial applications is, again, these Gdl and OGR tools. So there are plugins available or libraries available that will allow you to access all the Gdl and the OGR tools via Python, which is very useful if you want to integrate these geospatial tools with the more classical tools. So, for example, if you have a shapefile and you want to use that shapefile for some kind of machine learning applications, you can actually link all these different data types and data library sets and together and make very nice and very complex tools yourself. pproi, I use that for project transformations, and then some other more specific tools, Fiona for OGR, raster.io for Gdl, Shapely for the more the purely geometrical calculations that you can work there. Small application or small example of pproi. So pproi is a library that will allow you to transform data from one coordinate system to another coordinate system. And actually all the coordinate systems that are available in the EPSG repository can be accessed and can be used for these kinds of transformations. Originally, proi is a C API, so a C library, and pproi is actually a wrapper, a Python wrapper that will allow you to get access to the proi library itself. So if you are familiar with Python, you can use pproi to access all the functionalities of proi itself and do your coordinate transformations. And actually, the way of converting one data set to another data set in different coordinate reference systems is quite straightforward. It's a matter of importing your transformers from pproi. You define your coordinate systems using these familiar or famous EPSG codes. So this example here is going from Belgian Lambert 72 to Lambert 08 coordinate reference system. And then it's just a matter of defining your coordinates, do the calculation, and you will end up with the coordinates from Lambert 72 to Lambert 08. But you can do that for any types of coordinate transformations, of course. If you have your data in a manuscript plan, for example, in the Romanian system, and you want to convert that to UTM, yeah, in that case, you just change here the EPSG codes, make a loop for your coordinates, and you can convert entire coordinate list or coordinate data sets to UTM or to any other coordinate reference system. And another very cool thing about Python is that it's also implemented and integrated in QGIS. So PIQGIS will allow you to work in Python or with Python in QGIS to make your own plugins, but especially to automate specific processes. So for example, I'm currently working on a totally different project on spatial planning in Belgium. I have a huge data set with a lot of parcels, and then there's a simple question: what is the area of all the parcels that meet a certain criteria? Yeah, in that case, here I have example code here. You can use specific tools for that in QGIS, but it's very fast and very convenient just to use PIQGIS, get the data, get the geometries of all the data in that data layer, and then sum the area of all the different polygons. So this is a very simple example, but another example, another plugin that I built myself just a few weeks ago, was the calculation of the pedestrian side roads, of the pedestrian areas in the Flemish region. So you define an area on the map, and then based on a lot of open data, it will calculate the the width of a certain pedestrian area next to a conventional traffic road, so that municipalities can have an idea about the width and the accessibility of these areas. That's of course not a standard function in QGIS, but using Python in QGIS, you can really do that, to make these tools yourself and link different processing tools together. Point cloud processing. So let's continue with that. A software package that I frequently use for point cloud processing is the open source software called Cloud Compare. So Cloud Compare is a software package developed by a guy that did his research at Électricité de France, so the French national electricity company, and he developed that program for the visualization processing of large point clouds. So initially it was developed to work with laser scan data and to see how laser scan point clouds in situ are differ from as-built models, or sorry, from design models. So if you have a large construction in a 3D model in terms of building information model or in architectural software, and you have your point clouds, you can drape the point clouds on your 3D model, and then based on the distance differences between each individual point and the object itself, you can actually calculate differences between in situ and designed models. So it is heavily used for applications in emergency mapping, as-built documentation, but also landslide monitoring. And also use that software in land degradation project in Ethiopia, hydrology, and of course cultural heritage. It will allow you to do some basic manipulations, transformations, manipulations, segmentation, subsampling, cross-sections, and even point cloud registration. So if you have multiple point clouds, for example, measured by static laser scanning, you can actually use Cloud Compare to merge all these different clouds into one massive integrated point cloud where all the data are nicely stitched together. And here are some screenshots on the visualization of point clouds. So normally if you have a point cloud, just the XYZ point cloud that doesn't contain any information, yeah, of course you will get a white surface. Hopefully you will have some colors attached to each and every point in the point cloud. But even without other attributes assigned to your point cloud, you can do some point cloud enhancements by using shaders or calculate normals in your point cloud software development, software environment. So very straightforward for point cloud visualization, but also point cloud filtering, manual segmentation, but also the segmentation or the filtering of point clouds using geometrical constraints. So for example, this was a terrestrial laser scanning point cloud of the archaeological site of Eleusis near Athens. There was a plane fitted on this point cloud, and based on the distance between each point in each individual point and that best fitting local plane, we were actually able to do some outlier removal. So here you see the distances. So the more reds in the color, the larger the distance between the point and the best fitting plane. And if you make a histogram and you say, okay, let's eliminate all the lower 2.5% and the higher 2.5% out of this population, you can actually do very interesting and very fast outlier removal just based on statistical tools, for example. Some other things you can do with Cloud Compare is data transformation. So if you have a randomly oriented point cloud and you can identify a horizontal plane in your point cloud, you can just level your point cloud. Already mentions point cloud segmentation. So if you have a massive point cloud with millions and millions and millions and millions of points, and you're only interested in a small portion of your point cloud, you can use that for interactive segmentation. Export your point cloud, and then you will have a much smaller subsection of the data set. It's much more easy to handle. And then if you have your point cloud filtered and georeferenced, I would like to mention the ability to calculate cross-sections, slices, contours, all interactively. So for example, if you have a point cloud of an archaeological site and you want to derive sections at certain distances with a certain width, you can automatically extract them, export these features to a CAD environment, and then in CAD you can clean up the extracted polylines that are derived from there. Well, this is all based on data processing in a graphical user interface. There is an option in Cloud Compare to work with a command line. So the different tools that you can actually access, parameter settings that you can access with your command line, your terminal. By the way, Cloud Compare is available also for Mac users. But if you really want to have the flexibility of really working with variables in a certain data processing workflow, I would recommend to use PDAL, or the Point Data Extraction Library. Excuse me. Point Data Extraction Library, pdal.io, for more information, where you can actually translate and manipulate point cloud data purely based on a command line. So there's no memory assigned to your graphical user interface. Everything is just done directly in the command line. So we're talking about reading, writing, filters, translators, and querying all these points in your point cloud. Actually, it is similar to Gdl. So what Gdl does to vector data, PDAL does to point cloud data. And interesting to mention also is that it has some Python bindings. So a couple of months ago, I got point cloud data from an airborne UAV data acquisition campaign, and that data sets, I think it was almost 1 billion points in that point cloud. And I was asked to do some data extraction and data cleaning on that point cloud. I could use Cloud Compare for that, but it will only take me half an hour or an hour to load that point cloud in Cloud Compare or in any other software with a graphical user interface. So what I actually did was extract a very tiny portion of that data set, identified the certain characteristics of that data set, and then using that sample and extracting all the different parameters, I made a so-called pipeline. So a pipeline in a JSON file. So here you see an example of such a JSON file. And then by running PDAL with that pipeline, it can actually automate the different steps without loading all the data in some kind of a graphical user interface environment, but directly apply the different processing steps and processing tools on the point cloud without taking care of the graphical visualization of these data. So PDAL in that case, and I think if within the framework of the Sultana project, you're going to work with drone data and with massive point clouds, I think that especially for preliminary data processing, PDAL can be a very interesting tool to speed up a lot of data processing on that prior to the final data processing in other software. So for example, in this case here, I have an input point cloud, and the only thing it does here is calculate a digital elevation model, so a raster-based digital elevation model using inverse distance weight with a resolution of 10 centimeters and a search radius of 1 meter. This is the simple pipeline. You put it in your Gdl environment and it will automatically run, and it's significantly faster than doing that with a graphical user interface. Another thing that might be very interesting also for you to implement is, for example, to use Gdl for the extraction of certain spatial portions of your point cloud. So instead of loading the entire point cloud in Cloud Compare and then draw a polygon around a certain area and then extract that portion of the area, this is of course a quite time-consuming process, especially when you're working with billions of points. You can actually automate that, make a pipeline for that and say, okay, let's extract all the points that are situated in that polygon, and then the result will be a new loss file or a new point cloud file that is much more convenient, most probably, for further data processing. Then a little bit about conventional and linked data, where in a sense linked data may be a little bit misleading here, because the thing that I'm going to discuss here is actually an extension of another library of Python, GeoPandas, a tool that or library that I frequently use for spatial data processing in Python. Just today, I finished a little website where I extracted data from the dataset from the World Health Organization. I linked that with data from some kind of a geospatial organization, and I converted that to an interactive website where you can access the average alcohol consumption. I think it was all over the world. It was for a food monitoring project. And all these data can be processed using GeoPandas, the GeoPandas library for Python. It actually combines the power of a whole ecosystem of geotools. I'm talking about pandas for matrix calculations, geos for the more conventional, the more fundamental geospatial analysis, Shapely for geometrical processing or primitive processing, and then pproi data of coordinate transformations. So a very useful tool to read and to write various data formats using the Fiona and the Gdl OGR libraries, manipulations of attributes that we can do with the pandas library, spatial predicates, operations, reprojections, that's all possible and all integrated in this GeoPandas library. So it's very convenient, very useful if you're into Python for a lot of data automation. An example that I want to share with you, and that's recently been published in a book about the Toricos excavation, is this project that you see here. This is the Villaturi mountain, that is the mountain on top of the archaeological site of Toricos. It goes for many years, and various cultures were active on that mountain. And the last few years, archaeologists have divided that mountain in a grid system. The grid system was divided in a subgrid system, and then they said, okay, let's take 15 minutes to walk in a specific grid and take all the finds that are on the ground, situated on that ground in a specific cell, and then let's make a classification of all the finds. So it was how many tiles were found in a certain cell, how many amphoras, how many pitos, how many artifacts from the geometrical era, from the Roman era, from the Byzantine era. So you will end up, or we ended up with a huge database of different classification typologies, both temporal and thematic. And then using GeoPandas and Matplotlib, we were actually able to do or to automatically calculate density plots for many types of artifacts. So these little maps, are all based on pandas, making interaction with spatial databases, and the spatial databases are of course fed by the finds itself and the interpretation of these finds. So a very useful tool to do large-scale topographic of thematic mapping. So I was very happy to work with GeoPandas in this application. Of course, these data should come from somewhere. They should manage from somewhere. And a very interesting open source set for database management is PostgreSQL, also known as Postgis, free open source relational data management system, or DBMS, that is easily extendable by other libraries. And one of the libraries that I frequently use on top of this typical database management system is Postgis. So Postgis is a database extension on PostgreSQL that will allow you to define SQL. So it will allow me to do conventional querying on data in a database, in a relational database. But on top of that, it will also support spatial querying. So you see here a little example of some spatial queries that you can apply on data in that database. And by doing that, you can just define your own SQL code and do, instead of working with a conventional geographic information system or even with Python libraries, you can do that directly in the database itself. And especially if you're working with PostGIS and you are able to master some more advanced web development tools like PHP, yeah, you can actually combine these two and make fully interactive online environment applications using databases like that. So, for example, here you see an extraction of a screenshot of QGIS, where you can directly access your PostgreSQL database with PostGIS. Or more conventional database management systems like DB for PHP I also mentioned, and even Python is able to work with PostgreSQL. So you can actually write Python code to access data. Actually, if you look closely here, I think it's mentioned here. Yeah, here you see Zone SQL. This is actually an SQL code that is sent to a Postgis server, and the data is furtherly processed in GeoPandas. So actually, everything that I say here is related to each other, and that's why I really like this topic so much. Then the last series of software that I would like to discuss with you, that you might be more familiar with, is on image processing. By the way, I have to keep an eye on the time because I understood that I only have an hour speaking time. It's almost time.
It's okay, you can go on.
Okay, perfect. Yeah, I'm almost finished. Some of you might be familiar with Photoshop, and maybe your university has an agreement with Adobe that as a researcher you can have free access to Photoshop. At Hoogent, that's the case. So, for example, on my MacBook I have Photoshop, but on my Windows computer I'm running the GNU Image Manipulation Program, or GIMP, which is available for both Windows and Mac OS. So I used to have GIMP on my MacBook as well. It's actually a software package for image processing, as mentioned here in this title, but image manipulation, image editing, freeform drawing, transcoding between different image formats, image transformations. Let's call this a Photoshop Lite. It doesn't have all the functionalities, far from all the functionalities of Photoshop, but it comes very close to it. So if you look at the interface, here's a screenshot of an orthophoto, a TIFF file that I imported in my GIMP environment. You see here different, actually the look and feel and the functionality is quite similar to Photoshop. And of course, the biggest advantage of GIMP against Photoshop is that GIMP is totally free, open source. The drawback of it is that a lot of functionalities are not available. So, for example, time series and animations. To the extent of my knowledge, at least, these are not available, but maybe I should have a more closer look on that one. This is quite an interesting alternative. Also something, I'm thinking about it as we speak, people that are using Lightroom, Adobe Lightroom, there's also a very nice alternative for that software package. I think if I, it's called, I have it here. Yeah, raw therapy. So with raw therapy, you can actually do lens corrections and image corrections as if you would do it in Adobe Lightroom. Also, not the full functionality of Lightroom is implemented in raw therapy, but it's a wonderful start, and especially for a non-specialist on image processing or image photography, it's a very nice start to do some interesting things, write batches. Another thing that I used light therapy, for example, is white balance corrections and gray card implementation. So that's quite useful for that one. And then to finish, to software that can be used for 3D modeling based on images. So let's say alternative open source alternatives for Archisoft that is frequently used in that field. The first one, I have some experience with Mikmak. So Mikmak is actually a free open source photogrammetric suite that is being developed by the National Mapping Agency of France, the IGN, Institut Géographique National. And it offers actually a series of tools that you can use for image-based 3D modeling and orthorectification and DM construction. So if you can, as you can see here, it has some tools that are linked together. It has a graphical user interface. And I think 2 or 3 years ago, I made some practical sessions for my students to work with this software, and the results are actually quite nice. The only problem that I experienced here, and that's the problem with many open source software on 3D image-based 3D modeling, is that as soon as you're working with large data sets, so hundreds and hundreds of photos, and you want to work with these photos for orthorectification or even the image matching and the dense point cloud reconstruction, these tools are not that mature as you would expect with Archisoft. So image-based 3D modeling and open source software, it's really going in the good direction, but the maturity, as we have seen with GIS, for example, that level has not been reached that far. However, there are some other alternatives as well. Another interesting tool that I would like to mention, and it is definitely on my to-do list to test, is OpenDroneMap. So here you can find the URL for OpenDroneMap, open source project for processing aerial drone imagery. And the cool thing about it, as I read in the user manual and in different papers that are written about it, is that it also offers some kind of a web interface where you can just take your own server with a lot of GPUs somewhere remote, and then you can actually upload your images to that online environment. In the online environment, all the calculations will take place, the image matching, the feature extraction, image matching, dense point cloud, reconstruction, and the orthorectification and the extraction. That's all done on the server, and then the results you can just download. Actually, I will be very honest about it. I have no experience with ODM so far, but as a start, I think I will go for live ODM. It's mentioned on the website, a bootable DVD USB ISO with ODM, Node ODM and Web ODM pre-installed. So that actually means that if I download that package, I put it on a USB stick, a bootable USB stick, as soon as I plug in that USB stick at the starting up process of my laptop, it will actually start a new operating system from that USB stick, and I can fully test that environment. There's also a stick like that available from the Open Geospatial, no, not Open Spatial, the Open Spatial OSGeo organization. So the organization that is supervising a lot of open source projects on spatial data management and spatial data manipulation. They also have the OSM Live, the OSGeo Live ISO that will allow you to test the different software packages that are offered via their website. So I think that's a very good way to get started. Voila, here are some features that are mentioned on their website. So mosaics, point clouds, elevation models, 3D models. You can read it here. And I think also for the Sultana project, there are some very interesting things that we should test here. So for example, here, multispectral data processing. I think that's definitely something that we should have a closer look at. And I'm looking forward to get started with that. So voila, my conclusions so far. I hope that I made clear that open source had a lot of potentials and offers a lot of opportunities also for archaeological projects and digital humanities in general. So it is not always necessary to go to a commercial software vendor and ask for a good price, but just take the software, implement it, install it on your own computer and start experimenting with it. That's also the way that I explored a lot of these software packages. There's a very active community working on these different packages that will offer support and frequent updates. Availability for various operating systems, so Windows, Mac, Linux. There's actually a taste and a favor for, there's a favor for every taste, let's say. Many of these packages are offered with a graphical user interface, but frequently, even more frequently, you will have to need to have some skills in command line processing. Some little scripting is very good to get started with many of these projects. For example, if you want to work Gdl, I think it is really necessary to have some understanding of how batching and the command line in Windows works, or in the terminal in Mac. And another drawback is that, yeah, of course, there are many initiatives on open source software, especially for spatial data. So then it comes to the question, okay, what software should I use? What is the maturity, like I mentioned, for 3D modeling software for image-based reconstructions, and what is the learning curve? So it requires a certain effort to familiarize yourself with software. And in some cases, even after taking some time to get a better understanding of the software, it's not always that successful, and you will have to leave that software and look for another software. So it's a little bit of trial and error. But fortunately, and that's also coming back to the point about the large and active communities, there's a lot of documentation available. So if you start reading about software, you will actually quite fast, quite smoothly get a good understanding of at least what the software will do for you and how it will help you. To finish, I made a list of the different references. So if you want to experiment with these software packages, this offers you a nice overview on where to look for data, how to install the different software packages. For sake of completeness here, for example, the Python for QGIS library are available, and all the other software packages. And then to finally finish my presentation, I would like to make a little promotion for a specialist course on digital tools for cultural heritage management that is organized by the Heritage Management Organization in Greece. It will take place next month, so starting from the 17th of May until the 11th of June 2021. Unfortunately, or fortunately, that depends on how you want to see it, it's totally online. So last year it was also fully online, but the years before we had the pleasure to go to the city of Nafplio, the old capital of Greece. But in this case, and especially with the experience of last year, I think we have a wonderful program on GIS photogrammetry and image-based 3D modeling and laser scanning. So if you're interested in these topics, you're more than welcome to have a look on our website, heritagemanagement.org, or to contact the program officer to see how you can participate. So voila. Thank you very much for your attention. I really hope that that I can trigger you with my enthusiasm about this software, and that you will find some of the package very useful. If you have further questions, I hope there is still some time available for question and answer, for discussion. And otherwise, I'm looking forward to further correspondence via email or Teams or whatever. Well, thank you very much.
Thank you also. It was a very complex and very rich lecture, actually. Some points were more advanced than others, I can say. And actually gives us hope that we can do all this stuff in archaeology, not just thinking about how we're going to save it. We actually have tools to save our cultural heritage. And I was very impressed maybe about the things you did at Seira, the town that was on a shore, and you actually go with the tablet and start drawing the walls. And I like to do that on our site too, because it's very useful. As you know, we try to register everything we do around us in an excavation, and it's very important to do it right from the start. So processing is not that complicated. Sorry, I talked too much. If anybody has any questions.
Thank you very much, Cornelis, for this very wonderful presentation about the impact of different open source softwares. Sorry I missed your first part of your presentation, but it was impossible to be there because I should made some calls with the rector and other people, important people from the top staff of university, and you know how it is. Administration is the science. Always is the same. Okay. Everybody else, questions?
Well, I would also like to thank you, Katalin and Christina, for this wonderful opportunity that you've given me to talk about this topic. Especially the second part is a brand new presentation, so I made it the last days, and for me also it was a good way to synthesize the things that have been done. And it's a great pleasure to share this information with you. And I really hope that we will find some ways in the future to work with it together, especially with the new opportunities that you're exploring.
Yeah. Okay. Thank you. People, other questions?
I would have a small question, actually. You said you worked also in Mac and Windows. Do you see a big difference between these types of operation?
I was expecting yes, but the answer is actually no. The only thing, it's more practical, so it's not software based, but I have here my MacBook. I really love to work with it because the battery duration is amazing, and I can fully understand why Professor Lazar is so extremely happy about this MacBook, if not only for the battery that I will definitely not get with my Windows computer. My Windows computer, I'm working on a workstation, so it's not very comparable. But for the rest, I have my Word, I have my Agisoft, I have my Cloud Compare, I have my QGIS on both systems. Visual Code is working here, so most of the times I'm working on both computers at a time, sometimes even 3 computers at a time. And it's only annoying when I have to work on my command button, that the command button is the equivalent of the control button. So that's all. But for the rest, in terms of functionality, no difference at all.
That's good to hear for everybody who wants to use these softwares. Yeah. If that's...
There are, however, well, first of all, I think there are some points to stress out here. So many software are developed for Windows, of course. But if you go to GitHub, and there is a software package that is developed with a graphical user interface, most probably that graphical user interface will only work with Windows. So that's something to keep in mind. However, if you have these data, or if you have these code, frequently there's also a repository or a plugin or even a compiled version of that project that works under Unix. And Unix is actually the system behind Windows, behind Windows, I'm saying, behind Mac and behind Linux. So in some cases, the code without a graphical user interface can be accessed, or the program can be accessed via your terminal. If that is not the case, it is even possible to compile the codes on your MacBook with Homebrew, and many packages are available on Homebrew for Mac. So, for example, the Gdl libraries, I extracted them with the Homebrew repository on my MacBook, and that works exactly the same as I would have with Windows. But it requires some scripting skills.
Yeah, I was about to say that most of us are not so advanced on using this type of software. So basically, probably we'll start with QGIS, and from there we go to the next level. Yeah.
Well, I think, and that's maybe something to discuss later on in the near future. For example, a little course about the use of Gdl in a command line with an introduction to command line processing for Windows and for Mac, to get some idea of, okay, if you open your terminal screen on Mac or if you open your command line in Windows, what is actually happening there? Because when you have your graphical user interface and you click on a file open, that's exactly the same as what you would type in open, uppercase of quotes, the file name, quote, enter, then you're actually doing exactly the same, but you're typing it in or you're using a graphical user interface.
Yeah. Well, there are any other questions? And if not, we will...
I have a curiosity, let's say. If you want to write your code, your Python code in QGIS, but you want to use some libraries that are not default from Python, like matplotlib, NumPy, pandas, and so on, you actually can do this in QGIS, or is better to write your own code in an environment that it's only using Python?
Well, you're actually asking two questions here, and the answer on both is yes, it is possible. So if you go to your QGIS installation folder, you will see a dedicated separate Python distribution available there. And if you install pip in that, so the Python library manager or Python content manager, in that QGIS folder, you can actually download and install all the libraries that you want to use. So for example, a few months ago, I prepared an examination for my students on XML extraction, or an XML reader that is not by default in QGIS. And by installing pip, you can actually install these libraries. On the other hand, and that's the second part of your question, if I'm working on spatial applications and I'm using a lot of external libraries myself, I would just go with Conda and type my code entirely in Spider, and maybe not even use the QGIS libraries, but dedicated libraries from Gdl or GeoPandas. And then in that case, I would leave QGIS behind.
I understand. Thank you for your answers.
Thank you for your question.
Me again. You said you used the QGIS field on your phone, or your colleagues did? Because, yeah. Did you do it successfully? Because I know we have to install a plugin in QGIS called Margin. So you do your, no, I'm not, from your face, I'm not, because I didn't manage to do that. I didn't manage to use my phone or my tablet to use QGIS, and I found this example of a plugin. You install it on your phone and also on your no. Then how did it?
Not necessary. You make your wait. If you want, I can show it to you. The basic idea is you make your QGIS project with your references to online resources, with your shapefiles. You make sure that everything is in one folder, and that entire folder, you just copy it to the internal memory of your smartphone, not on your SD card, but on the internal memory of your smartphone. And then from QField, you can access that project.
Okay, got
That's it.
Yeah, I did it a bit complicated, so
you don't need no need for plugins. Just prepare your project, make sure all the data is in the same folder, all the references are set correctly in the same folder, and then just copy paste it to the. That's quite important. The internal memory of your smartphone.
Great, thank you for the.
And another thing, my colleague was working on Android 8.
Okay.
And the project, so the default project was working. So the demo on B's, I think it's a B documentation. But the project I prepared was not compatible. And then he updated from Android 8 to Android 9 or 10. And then the project was working.
Okay. Yeah. Good to know. Thank you very much.
You're welcome.
Yeah. Does anybody else has questions? Well, if not, thank you again for this presentation, and you can find it online after we finish. And again, hope to see you soon to do a lot of processing and analysis.
Would be wonderful.
Yeah.
Okay. Thank you, Cornelis. We keep in touch via email or WhatsApp regarding our common projects. And thank you again. Keep in touch. Yeah.
Looking forward to keep in touch. Thank you very much for this opportunity.
Bye. Thank you. Bye-bye.
Have a nice day. Bye, Cornelis. Everybody. Thank you.